Hey everyone, welcome. Today we're diving deep into something that's at the absolute heart of Linux, but it's something we often take for granted: the file system. It's the invisible architect that keeps everything from falling into total chaos. So let's get into it.
Have you ever really stopped to think about it? How does a system that runs on everything, from a tiny little Raspberry Pi in your drawer to the biggest supercomputers on the planet, manage all that data so perfectly? It sounds like it should be an impossible task, right? But the solution is actually really beautiful.
The secret? It all comes down to a simple, brilliant analogy. The Linux file system works just like a massive, perfectly organized library. Every single piece of data, every file, has a specific place to live, a clear purpose for being there, and a system for finding it instantly. This library idea is going to be our map as we explore how this all works.
Okay, so if we're going with this library analogy, what's the first thing any good library needs? A blueprint, right? A floor plan that tells you exactly where to find the science section, the history section, all of it. In Linux, .blueprint has an official name: the File System Hierarchy Standard, or FHS for short. Now, the FHS isn't just a friendly suggestion. It's more like the official rulebook that nearly every Linux distribution agrees to follow. And that's huge. It means that whether you're on Ubuntu, Fedora, or Arch, you know where to find things. The configuration files will be in the same place, the user programs will be in the same place. You can think of it as the universal Dewey Decimal System for our digital library. And where's the front door to this massive library? It all starts at one single point: the root directory. And it's represented by just a single /. That's it. Every file, every folder, every single hard drive you connect, it all lives somewhere under this one single slash. And this is where that blueprint really comes to life. Let's take a quick tour of the main sections. Think of the /bin and /sbin directories as the librarian's own toolkit. It's where all the essential commands that run the system are kept. /etc, that's like the head librarian's office. It's where all the important system-wide configuration files are stored. Now, /home is where you live. It's like a collection of private reading rooms, one for each user. Then you have /var, which is the library's ever-changing activity log, full of things like log files. And /tamp, that's just the scratch paper and sticky notes left on the tables, a place for temporary files that don't need to last. So our library has a fantastic layout. But what happens when we get a new shipment of books? You know, a whole new collection we need to add. In Art World, that's like plugging in a new hard drive or a USB stick. How do we add a new bookshelf to our library?
Right, you can't just shove a new bookshelf in a random corner and hope for the best. There has to be a formal process, a set of instructions that tells the main library exactly where this new shelf belongs and how it should be treated. And that set of instructions lives in one of the most important files on the system: /etc/fstab. That just stands for File System Table. Think of this file as the library's master assembly manual. It contains the precise instructions for mounting, which is just a fancy word for connecting every single storage device every time the computer starts up. Now, if you look inside the fstab file, it can look a little intimidating at first, but don't worry, it's actually super simple. Each line is just a set of 6 instructions. The first part says what to connect, like a specific hard drive partition. The second says where to connect it in our library. The next few parts describe its format, any special options, and backup settings. And that last number just tells the system if and when to check it for errors. See? Simple, powerful, and very precise. But here's the really cool part. fstab isn't just for convenience. It's a huge security tool. With a simple option, you can make a bookshelf read-only, which is like putting a do not touch sign on it. Or you could use the no exec option, which says, sure, you can read the books here, but you absolutely cannot run any programs from this shelf. It gives you incredibly fine-grained control over your entire system. Okay, so we've seen the big picture layout of our library and how we add new shelves. But now, let's pull out the magnifying glass. I want to zoom all the way in and look at just one single book, or in our case, one single file. What is a file, really, to the system? To you and me, a file is its name. We see report.txt and we know exactly what it is. It's simple, it's human-readable. But here's the twist. To the Linux kernel, the brain of the whole operation, that name, report.txt, it's just a convenient label for us humans. The system knows that file by its true identity, its unique serial number, its inode number. So what on earth is an enode? Well, it stands for index node, and it is, for all intents and purposes, the official card in our library's card catalog. The file name we see is just a handy reference that points us to the right card. The inode is the card, and it holds all the critical metadata about the file. So what's written on this card? Pretty much everything. The inode knows the file's size, who owns it, what permissions it has, who can read it, write to it, or execute it. It keeps track of all the important timestamps, and, most critically, it holds the pointers, the literal addresses on the hard disk that tell the system exactly where to find the actual content of the file. The inode is the treasure map.
All right, our library is this beautifully organized machine, right down to the info on each catalog card. But life is messy. What happens when the system crashes or a disk starts having problems? Well, that's when we need to call in our diligent librarian to do a little cleanup.
In our library, this might be a catalog card that gets damaged or a book that's just gone. In file system terms, this means a corrupted inode, pointers leading to nowhere, or chunks of data that aren't connected to any file. These are the kinds of errors that can cause real data loss or even stop a system from booting up at all. The tool for this job is called fsck. It stands for File System Consistency Check, and it is an absolute lifesaver. This is our librarian. fsck meticulously scans the entire file system, compares the records on the inodes to what's actually on the disk, and fixes any problems it finds. It's the one who makes sure every book is exactly where it's supposed to be.
But fsck is an incredibly powerful tool, and it comes with one non-negotiable absolute golden rule. You cannot, under any circumstances, run it on a file system that is currently in use. Think about it. You wouldn't try to repair a bookshelf while people are actively taking books off and putting them back, would you? It would be total chaos. You have to close that section of the library first. You must unmount the device.
So, the safe procedure is always the same, and it's just 4 simple steps. First, you identify the device that needs a checkup. Second, and this is the most critical step, you take it offline using the unmount command. Third, you run fsck and let it work its magic. And finally, once it's given the all clear, you just remount it and it's back in business. Phew, we have gone all the way from the 30,000-foot view of the library's blueprint down to the nitty-gritty of repair tools. So, why does all this matter? Why is it so important to understand these rules of the library? Well, this is where all that theory turns into a real-world, practical skill. Because knowing this stuff isn't just academic. When your server suddenly won't boot, you'll know to check fstab. When you need to harden a system's security, you'll remember those powerful mount options. Running out of disk space, you'll know that var is the first place to look for runaway log files. I mean, this knowledge is fundamental for troubleshooting, for security, for performance tuning, even for digital forensics. It's a core skill. So we've built this incredible library. It's organized, it's efficient, and we even have a diligent librarian to keep it maintained. But what about a real disaster? How does our library protect its books from a fire or a flood? How do we protect our precious data from being wiped out completely? Well, that opens